Swayam Prabha. Digital India. Educated India.
All right, good morning, good afternoon, and welcome back to our series of lectures on analysis and design of rigid pavements. We've been covering Module 2, which is analysis of rigid pavements using classical methods. Now, as a reminder as to what are classical methods, we basically mean old, but what that means is that they are analytical methods, closed form methods, more importantly, methods that don't require any sophisticated computer programming in order to implement. So you get some nice formulas over here by which you could calculate whatever you're interested in to calculate. You could calculate stresses or displacements, etc., using, let's say, a calculator. You could do it by hand if you're a little adventurous, or you could program it on a spreadsheet. But you don't need any sophisticated mathematical tools as such in order to calculate them. Now, within Module 2, what we just finished before this lecture, we had a series of 3 lectures that went into the analysis of joints and dowels. There, I introduced you to the concept of joints. Why do we need them? How do we construct them? And then we went through dowels, where we looked at one of the, besides Westergaard's theory, we looked at another celebrated theory in JPCP sections, namely Freiberg's theory and the Freiberg equation, which was used to calculate the bearing stresses in dowels. And then we saw how to compute them. We saw certain intricacies when we are analyzing not one dowel, but a system of dowels, and how those can be used to analyze whether we have failure. In particular, we saw that dowel concrete interaction is perhaps one of those rare cases in pavement engineering where the failure mechanism is actually in compression instead of being in tension. Although in every other case that we'll see, the failure mechanism is basically in tension. Now, as a reminder, there are largely four types of rigid pavements. That is jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRCP, and pre-stressed concrete pavements, PCP. And in this course, we are basically going to study jointed plain concrete pavements, JPCP. They're called plain because there is no steel reinforcement inside the concrete. They are jointed because it's not just one large continuous piece of concrete. There are joints placed inside it, which are purposely made and purposely cut. And then to enable load transfer across the joints, we do add steel bars, dowels, or tie bars. Now, that's what we looked at last time. In Module 3, we will see some more sophisticated techniques to analyze joints and dowels. But before that, we are still on Module 2. And what we're going to do now is we're going to make a slight detour to talk about certain other important effects which lead to development of some stresses and therefore affect the performance of JPCP. Those effects are broadly on the line of climatic effects. Now, one thing to keep in mind is pavements, I think this is very obvious, but pavements are kept outdoors. So if it's raining, if it's hot, if it's cold, whatever type of weather that we experience, that all of us know instinctively what type of, whether it's a hot day or a cold day, the pavement has to be outdoors. The pavement has to withstand all those sorts of weather and climatic effects. And so it is very important for us in trying to analyze rigid pavements, in trying to characterize the performance of rigid pavements. It's actually very important for us to be able to understand what are the different climatic factors that a rigid pavement is subject to. How do they react to those climatic factors, particularly what type of stresses are developed as a result of those climatic factors, and how do we calculate those stresses. So what we're going to begin right now is a series of 3 lectures that are going to go into climatic effects on rigid pavements. Today's lecture is more of an introductory lecture in nature, so we're not going to do too many mathematical calculations and equations, but in the next 2 lectures, we'll actually go quite deep into a lot of mathematics. But for this lecture, the main learning objectives are, we want to explain how rigid pavements interact with the environment, and I want to particularly define and list something called thermal and optical properties of concrete. Again, I assume all of you have taken some course in concrete technology, at least a basic lab, since you have a civil engineering background. So you've probably know something about concrete. But usually in those classes, you don't learn about thermal and optical properties of concrete. many people in mechanical engineering might learn that. So if you have a mechanical background, you might be somewhat familiar with this, but maybe not for concrete. In civil engineering, generally, we don't have too much of a background in this. So that's why I wanted to take some time out to talk about this. But first, let's go into a brief discussion just to get started with this. When I say the word climate, what would you consider as climate? So, for example, this is a very common statement you'll hear: India has a very hot climate, or India has a very dry climate. Now, depending on what time of the year you're listening to this, that might be quite true. It might be quite hot and dry. Or it might be wrong. It might actually be raining cats and dogs outdoors. And it might be quite cold. Maybe you're wearing a sweater as a result. Maybe you're on the coast where certainly it might be hot, but it's definitely not dry. Or maybe you're up in the mountains somewhere where it is dry, but it's not exactly hot. It's quite cool. What do we mean by the term climate in that case? And in particular, what do we mean by weather and how is it different from climate? So maybe you'll hear IMD forecasts saying that, okay, the weather tomorrow is going to be rainy. The weather tomorrow is going to be hot. The weather tomorrow is going to be cold. Compare that with the statement I started with, that India is a hot, dry climate. What is the difference between these two statements? If today it's hot and tomorrow it's raining, then how can I say that the place I live in is hot and dry when the weather is changing every day? Furthermore, do we design for weather or climate? I pointed out in the beginning that these JPCP pavements or these rigid pavements, they are outdoors. They are going to be subjected to all the environmental factors that we just talked about. What do we design for? Do we design for these day-to-day changes, or do we just design for climate? And in that case, which climate? The climate of the past or climate of the future? These are some things which, as civil engineers, maybe you've never thought about before, but it's actually very important now more than ever due to climate change for us to have a good understanding of the answers to these questions. So let's go to the first question first. What variables would you consider under the term climate? Okay, I just gave you some examples: hot and dry, wet and cold. So maybe temperature is one variable. So, and by temperature, I mean air temperature. Maybe temperature is one variable. Another variable could be, for example, precipitation. That's rainfall. Or it could be humidity, which is, even if it's not raining, you still have some moisture in the air. So, humidity. Maybe sunlight. That is how much sunlight is falling. Maybe cloudiness, which is related to sunlight, but not exactly the same thing. These are a variety of variables that when you say the word climate, maybe these are the variables you're thinking about, of which air temperature is probably the most important one that you see talked about quite a lot today, but it's not the only one. For some of you who live in certain parts which are colder, maybe you are also thinking about frost or snow. That's also a possibility. So when we talk about climate, we basically mean the values of all these variables which I've highlighted here. But then the question is, what is the difference between weather and climate? If it's hot today and raining tomorrow, if it's dry today and raining tomorrow, if it's hot today and cold tomorrow, then what's my climate? Weather is what we call a short-term phenomenon. So I'll write it here. So this is a short-term phenomenon. Weather changes not just every day to day, but it changes hour to hour. In the morning, it might be relatively cool, maybe a little bit windy. By the way, in this list, wind speed also I would add to list of climatic variables. So weather is something that would change not just day to day, but hour to hour. The morning might be cool and windy, afternoon might be hot and dry without any wind, and by the evening, maybe it starts raining. So in the same day, you can experience completely different weather patterns. Climate is what we call a long-term weather phenomenon. Now, that's sort of hand waving. So when we say short term, we mean every hour or every day. What do we mean by long term? It's a really long time. But climatologically, as a scientist, what you mean is it is the average of 30 years of weather. 30 is the key term over there. So when we say climate, mathematically what we mean is we are interested in the 30-year average of whatever value we are looking at. So for example, let's say we have a particular term, which is a useful term, the average daily air temperature. That is, what was the average temperature of the air during one particular day? You will have some value today, you will have some other value tomorrow. If you wait 3 months later, you will have some other value. If you take an average of those for every day in the previous 30 years. That is what we would call the climatological value. That is the climatological average daily air temperature. So, from a weather perspective, the average daily air temperature changes every day. Climatologically, we generally assume, but it's not a very good assumption anymore, we generally assume that the climatological value is going to stay stable. That over the past 30 years, if we have certain value of the average daily air temperature, then the next 30 years, we're going to have the same value. This assumption that the past climate is representative of the future climate has a particular term. This is called climate stationarity. Stationarity, which is just to say that the patterns of the climate is remaining stationary. This is a general assumption we make in pavement engineering. So, to answer the last question, do we design for weather or climate? Well, when we design a rigid pavement, we certainly don't want to have to do it again in one more year or one more month. When we design it, the service life of a rigid pavement is typically 30 years. It could also be 50 years. CRCP, for example, is usually designed for 50 years. And as I had mentioned way back in module 1, it's not even that we expect the pavement to deteriorate and disappear after 30 years. We keep doing rehabilitation, and so the pavement basically goes on more or less forever, effectively. And so when we are analyzing the effect of environmental variables, which are all these things I've listed over here, when we're analyzing the effect of environmental variables, we are basically looking at climate because we are interested in the long-term behavior of the pavement, the long-term performance of the pavement over 30, 50, and even more years. So to answer the last question, do we design for weather or climate? We design for climate, but in order to get to climate, we have to account for day-to-day variations in the weather. And do we design for past or future climate? Historically, the practice all over the world is that we design for past climate with the assumption that past climate is going to be representative of future climate, which is the assumption of climate stationarity, which I just pointed out. It's not a good assumption. Climate is changing. It is actually changing much faster than we expected. So the last 30 years is not going to be like the next 30 years. So it's not a very good assumption. Nonetheless, due to force of habit, due to lack of data, due to lack of models, basically that's the assumption that we go by. Of course, there's a lot of research, including being done by my research group also, where we are trying to overcome these assumptions and try to provide better recommendations for how to manage climate for pavement management. But that's again more in the realm of research. So to summarize everything we learned in this important slide, what variables do we consider as climate? It's all these variables which are highlighted here: air temperature, wind speed, air temperature, humidity, sunlight, cloudiness, etc. All of these come under the umbrella of climate. All of these have an effect on the performance of the rigid pavement. When we analyze performance of rigid pavements, we are not interested in 1 month, 2 months. We are interested in 30, 50 years and maybe even longer. So effectively, we design rigid pavements for a particular climate. But in the process of designing for a particular climate, we have to first understand how weather is changing day to day before we reach the point of what is the general climate of the location where the rigid pavement is being designed. And when we design the rigid pavement, we design for past climate because that's all we have the data for, with the assumption that the future is a good representative of the past, which is not the case. So, and that is one shortcoming in where we do rigid pavement analysis and design. Okay, so let's say I ask you that, can you tell me, depending on wherever you happen to be living, can you tell me what is the average daily air temperature for the last 30 years of the location where you're living? Well, the short answer is most likely you will be able to get the answer. So where do you get the answer? There are basically two types of data, which is ungridded and gridded data. So if we consider, I'm going to draw a very, very crude map, but if we consider the map of India, again, this is very crude, not to be taken as representative, but if we consider a crude map of India, we actually have in India a series of weather stations. Usually you'll find it at airports, but there are other locations also. You have a series of weather stations which are run by IMD, the Indian Meteorological Department, as well as other private agencies also. So they can be anywhere. Wherever it's convenient, they can be placed anywhere at all inside the country. In other words, if I actually just on a map, if I put a pin for each point where I have a weather station, there is no pattern to it. It's a pretty random set of points because it's dependent on local conditions. Such a distribution of data then is called an ungridded data. It's a data set which is just randomly distributed in space, not in a regular pattern. That's what we call ungridded data. That ungridded data can be obtained in the form of AWS. This is automatic weather station. So A is automatic weather station. So each weather station, which is an automatic weather station, will record this data. It is possible through various means to get that data through IMD. There is also a particular network called ASOS, which is just a collection of the AWS data from a variety of locations, not just in India, but around the world. So if you're looking for ungraded data, which is just the actual weather station data placed almost randomly, not randomly, but essentially anywhere without any spatial pattern, then we call that ungraded data. That's also observational data. That's data that has actually been observed, that has actually been measured. There is another data set which we can call historical forecasts. So if you actually go to IMD's website today, which all of you can do, you will actually see a forecast, let's say for the next 5 days or for the next 10 days. It will tell you in the next 5 or 10 days, this is the average air temperature for each of these days, which is expected. You can also get minimum, maximum temperatures, etc. When those forecasts are done, those are done using certain computer models. And in those computer models, again, if we have this map of India, then the values are actually calculated at an evenly distributed set of points all over the country. And actually, the forecast is done beyond the country. It's actually done for the entire subcontinent. So we have these set of points which are at a regular distribution spatially. That is, they are distributed whether in the x direction or in the y direction. You have a regular set of points. That regular set of points is what we call a grid. So the historical forecast you can also get from IMD. They are called gridded data. So you will not be able to get a data point at any random point. You'll only get it at a discrete gridded data. Generally, those grids stay constant over time. That is, the gridded data from last year will be at the same spatial position as the gridded data from this year. Whereas with automated weather stations, they can move around. Depending on the convenience, depending on where the location is, they can move around in several places. There is one more source of data, which is called reanalysis data. Reanalysis data is basically when we go back in time and we run some numerical models and we run them in such a way that the prediction of the numerical model matches the observed data. So this is a combination of a forecasting technique as well as observational data. As I'm sure all of you are aware that forecasts generally may not be very accurate with observational data. Sometimes they'll predict that it's going to be a rainy day and actually it doesn't rain at all. I'm sure all of you have experienced this at some point. That's basically the difference between forecast and observational data. Reanalysis data is when we go back, we look at our previous observations, and then we modify our numerical models such that we match those observations exactly. Then the gridded data we get out of that is called reanalysis data. So reanalysis and historical data are both numerical data. They will have some amount of error contained in them. Observational data is, well, it's observational. It's actual data which has been measured. It's not to say there's no error. There can actually be quite a lot of human error in observational data and a lot of cleaning is required. But generally, there are no additional mathematical assumptions put into them. What are some sources of reanalysis data? There are actually many sources of what are called products of reanalysis data. There is something called MERA2, which generally comes from NASA. There is ERA5, which comes from the European agencies. And then IMD has the IMD-AA, which is actually based on the monsoon mission, but we also have a reanalysis product for the Indian subcontinent. So to answer the question of, if I ask you that in the last 30 years, can you tell me the average annual air temperature? You can look up any of these sources, whether it's observational data, which is ungridded, whether it's a historical forecast, which is gridded, or whether it's a reanalysis data, which is also gridded. You can look up any of these sources to try to answer the question. So that's the sources of various sources of weather data which are available to us. Based on those weather data, what I have here is a couple of maps. Now, these are taken from a variety of papers, and those papers I have cited below the figures. I just wanted to show you these maps to give you a sense that India is a pretty large country. And when we're talking about climate, we have a lot of variety when it comes to climate for each of these climatic variables. So the one which we've been talking about so far is average annual air temperature. So this map which I have over here actually shows the average annual air temperature for different regions in India. And as you see, there is a fair amount of variety. The lowest average annual air temperature is in Ladakh. No surprise. That's the high Himalayas. Also Sikkim and Arunachal Pradesh. Also not a surprise. Just below that, we have the foothills of the Himalayas. So that could be, for example, in Himachal Pradesh, in Uttarakhand, also in the lower parts of Arunachal Pradesh, as well as Sikkim. And then you have a little bit cooler parts, let's say in the northeast or just in the foothills of the mountains. Then when you start coming into the plains, or in addition to foothills of the mountains, also here in the Western Ghats, you're going to have somewhat cooler weather. And there are a large number of hill stations also in this place for that exact reason. Come further down into the plains, you start getting these orange shades. That's why it's significantly hotter. And then you reach here along the east coast as well as here, say along Gujarat, where you have the highest average annual air temperatures. So as you see that within our country, we have a large geographical variation in the average annual air temperature. Another variable we might want to look at is the average annual precipitation. This is not entirely on account of the monsoon, but what you can see over here, the highest average annual precipitation can come here in the Western Ghats, as well as in Meghalaya over here. Perhaps many of you have heard of a place called Cherrapunji, which is the wettest place in the country. And this map shows you also that Cherrapunji is not just the wettest place in the country, that whole region in Meghalaya gets the highest amount of average annual precipitation. The lowest amount of average annual precipitation, no surprise, basically comes in the Thar Desert. Also comes in Ladakh, which is a cold desert, where you also don't get a whole lot of rain. And then you have other variations, whether in East Central India or in West Central India, you have different amounts of rainfall. So you see that even when it comes to average annual precipitation, we have a lot of variety within the country. And then finally, I wanted to show an interesting graph, which is also very relevant to pavement engineering, on average annual solar radiation. Now, for those of you who have a little bit sense of geography, you might think that, well, average annual solar radiation should just be a function of latitude. So closer you are to the equator, more solar radiation, further away you are, less solar radiation. That's correct. But there are certain variances, and those variances come due to clouds. So some places get more clouds than others. So there is a distinction between the theoretical amount of sunlight that a location would get based on its latitude and the actual amount of sunlight that it gets because of cloudiness and local conditions related to humidity. So based on that, this graph which I have over here, which I've taken from NREL, which is an American agency, this graph which I have over here, it shows that the lowest amount of annual solar radiation, no surprise, actually comes in the Himalayan regions, so up in the high mountains. And the highest amount, again, no surprise, it comes in the Thar Desert, it comes in Gujarat, it comes almost in the entire Deccan Plateau with the exception of the Western Ghats. And then somewhere in between you get in the Indo-Gangetic Plains in between. Now, as we shall see, this solar radiation is very, very crucial to the performance of rigid pavements. In particular, it relates to a particular term called the albedo, which we'll define today. And so it's very important for us to understand, when we're trying to understand the performance of a rigid pavement at a location, we must have a very good idea of how much solar radiation do we actually get at that location and how do we account for it. So in these three slides, I wanted to show you that there is not just that what is climate and what is weather, but that India is actually a fairly large country and we have many changes in weather patterns or climate. For example, in annual average air temperature or precipitation or solar radiation. We have a large variety in how these items or these values vary spatially across the subcontinent. All right. So now let's talk about the climatic effects on rigid pavements. In particular, I want to first talk about precipitation. In short, rainfall. I want to talk about how does rainfall, or when it's raining a lot, how is it going to affect the performance of rigid pavements? Now, one thing to remind yourselves is the rigid pavement is basically a slab of concrete. Concrete under ideal conditions is impervious. That is, it does not allow any moisture to ingress or go through it. So ideally, under ideal conditions, of course, you do have a joint also. And as I mentioned, the joint should generally be sealed. So we do apply a sealant. So if the sealant is applied properly, ideally if we have very well applied sealant, and I want you to go back to the previous lectures when we had a discussion of what is a good sealant and how do we apply a good sealant and what's our deterioration we can get in joints due to poor sealants. I won't repeat all that. But if we have a well-made concrete pavement without any cracks, if we have a well-sealed joints, then under those ideal conditions, it doesn't matter if it rains. So as such, rigid pavements tend to be fairly resilient if they're designed properly, if they're maintained properly, they are fairly resilient to precipitation. But then we should always ask, whenever we talk about ideal conditions, we should always ask ourselves, are conditions actually ideal? Well, that's not the case. A typical rigid pavement, and again, if any of you live near a rigid pavement, I encourage you to go outside and look at this for yourself. A more typical rigid pavement will have some amount of cracks which have developed. It develops over time due to a variety of reasons. So, a rigid pavement will have some amount of cracks which have developed. The joint itself, it's possible that the sealant has broken off, the sealant has deteriorated. And so what happens is you have through cracks as well as through this exposed joints, you have a path for ingress of moisture into the base layer as well as the sub-base layer. And below that, the subgrade layer. Now, if it just rains a little bit, it might not cause too much of a difference. But prolonged exposure to precipitation, and again, we're talking about the pavement having to perform for 30, 50, and more years. So even a couple of days of flooding a year can over time add up to a lot of to a prolonged exposure. So prolonged exposure to precipitation can lead to a lot of moisture being collected inside the base, sub-base, or subgrade. That can cause pumping. So we talked about pumping in an earlier lecture, that basically if we have the approach slab and we have the leaf slab, and on the approach slab we have a load, and now what we have is we have a situation where we have a lot of moisture in the base layer. So when the load is applied here, this slab pushes downwards, and then when the load moves onto the leaf slab, this slab goes back up, and so you have a pumping situation where water is being pushed up and pushed down, and eventually water as well as fines is simply going to be ejected through the joint. That's a situation what we call pumping. So prolonged exposure to moisture can lead to pumping. Over time, what pumping does is it creates a void underneath the slab. That is, all the material which is at this part underneath the slab, it basically gets ejected out or pushed outwards, and you're left with effectively a hole in the base layer. When you have that type of situation, then the slab is no longer sitting on a set of voids. The slab is actually sitting on nothing. It's sitting on a void, and so you have what is called loss of slab support. All our assumptions which we made so far in plate theory assume that the plate is sitting on top of a bed of springs. If we do not have a bed of springs in a particular location, then very high stresses can develop because we have an unsupported slab at that point, and that can lead to very rapid deterioration of the slab. That's under some conditions, that's how we get corner cracking and certain other phenomena, which we talked about in module 1. So prolonged exposure to precipitation, ideally, if the pavement is in ideal conditions, it does not make a difference. But pavements are never in ideal conditions. So in practice, if water is allowed to stagnate on the pavement for a long time, we will start seeing problems related to pumping and loss of moisture support. And these are therefore climatic effects. You will note that while pumping requires the presence of a load, the loss of moisture support, however, does not require the presence of a load. So the pumping generally is caused largely due to a climatic effect, also although an external load is also required. So that's the effect of prolonged exposure. But is prolonged exposure the only part where we take moisture into consideration? Keep in mind, when we talked about precipitation or moisture, I mentioned that, well, precipitation is certainly one aspect of moisture. That's when we get a lot of rainfall. But there is also some amount of moisture in the air itself, which is what we call humidity. So there is some amount of moisture in the air itself. Does the humidity of the location also affect the performance of the pavement? It turns out the answer is yes. Why? Let's consider early age concrete. Again, I've assumed all of you have taken a class on concrete, so you probably know that when you begin to mix concrete with concrete is basically cement, aggregates, and water. So when you first mix the cement, aggregates, and water together, it's a fluid-like substance, right? It's not water, but it's some type of fluid. So it's a fluid-like substance which which basically flows without having any, which has a flow rate. So basically the shear stress depends on the strain rate. So that's what we call early age concrete. Over time, as ettringite forms and setting starts to happen, it goes from becoming a fluid-like material to an elastic or a quasi-brittle material. That generally happens over the first 3 days. So when we say early age concrete, we basically mean concrete in its first 3 days. During that period of time, even as the concrete has set, that is, ettringite has formed and it's starting to behave more like an elastic material, but at that point of time, the concrete is very weak. As we know, it takes around 28 to 90 days for the full compressive strength, or almost the full compressive strength, to develop. So, in those first couple of days, although the concrete has set and the concrete is behaving as an elastic material, the concrete is extremely weak. In that case, what happens is, now if I look at the cross section of the concrete has to have water in it for the reaction to happen. So generally, I can assume that the concrete is basically saturated, which is the relative humidity is say 100%. Now, outside the relative humidity can be any other number. It depends on the location you're in. So if you're in the coastal areas, the relative humidity might be 98%, very, very humid. Or if you're in a dry desert type of area, it can be as low as 40%. So you have some external or ambient humidity, and then the concrete itself, initially at least, is completely saturated. So relative humidity is 100%. So what happens is then at the surface, you have a very sharp gradient of humidity. So just below the surface, at a very small depth below the surface, you have 100% humidity. Above the surface, you have whatever is the ambient humidity. This sets up a moisture gradient near the top of the surface. Now, what happens is, in response to the moisture gradient, some amount of stress, tensile stress, is going to develop, which is caused when you have a high moisture gradient. So, if we don't do any sort of control on this high moisture gradient, then we can start having some amount of cracks, which are called shrinkage cracks. We can have some amount of cracks developing. There is another source of shrinkage cracking, which is basically the moisture inside the concrete is also getting used up by the hydration reaction. So that's also creating a moisture gradient. So that's another source of shrinkage cracking. Now, this shrinkage cracking, in the long term, it might not be a big deal because the actual stress is relatively small. But in the first 3 days, at the early stage when the concrete has not developed too much strength, then these strains can actually exceed the strength. The stress can actually exceed the strength, and in that case, you'll start having cracks developing, which are called shrinkage cracks. So we need to be able to control this. At least in the first couple of days, we need to be able to very strongly control the development of shrinkage cracks, which is done by controlling the development of moisture. It can be controlled, for example, through curing. Now, there are many ways of curing, which we'll talk about. One way, which maybe many of you have seen, is by just putting a wet jute bag on the surface. Sometimes, in some parts of the world, that wet jute bag is also called burlap. So that's one way to control the development of shrinkage cracking, by controlling curing. Now, so that's one aspect of climate. So when we look at climate, and there when we look at moisture, we saw that long-term exposure to moisture, which is precipitation, could have an effect on rigid pavements if the rigid pavements are not ideal, and almost always they're never going to be ideal. But even in the short term, that is in the first couple of days of the life of the pavement, if you have a humidity or a moisture gradient and that is not controlled, that is, we have not put some wet jute bags or done anything to control the humidity and the moisture gradient, then we can have some shrinkage cracks also developing. So that's one effect of climate on rigid pavements. Another effect on climate on rigid pavements is through temperature distribution. Now, the concrete, as we know, is kept outdoors. So what is it exposed to outdoors? Obviously, you have the sun. You have the sun, which is continuously beating down on the pavement. You also have some wind. You also have some clouds. All of these are going to establish some type of temperature distribution inside the slab of the concrete pavement. The temperature distribution, as it turns out, actually happens during day and night. So regardless of whether it's day and night, we will have a temperature distribution, but the nature of the temperature distribution is going to be different. We'll talk more about it in the next lecture, which is lecture 12. But for now, what you should know is that the temperature distribution inside the concrete pavement has been empirically shown to be non-linear. So, and generally, as we'll see, it tends to be more quadratic in nature. So you have a non-linear temperature distribution, but it is a constantly changing temperature distribution. So as the angle of the sun is changing, as the air temperature is changing, as wind is changing, as cloud cover is changing, etc. So basically, as the weather is evolving, then the temperature distribution through the pavement is also changing. Now, one challenge I'll leave you with, whose answer I'll actually give you in the next lecture, not in this lecture, is this figure I have over here is actually taken from some of my earlier work. In this figure I have over here, I've shown you Z over H is on the y-axis. So here Z represents the depth from the neutral axis or the neutral plane, So if this is my concrete slab and here is my neutral plane, which is going to be at h over 2 in case we have a plane section, which is what we have in this case. So below going downwards here, we've got z. So z actually goes from minus h over 2 to h over 2. And that's why what I've shown over here in this graph is that z over h, I've just non-dimensionalized it, it goes from minus half to plus half. So basically you're seeing a figure where this is the bottom and this is the top. So what you're seeing here is a figure showing the distribution of the temperature through the cross section of a rigid pavement. On the x-axis, I've got temperature in degrees Celsius. So what I've shown here is I've shown a couple of different possible distributions, which are all ones which I developed during some of my work. The question I'll leave you with, which I'm not going to answer in today's lecture, I'll answer in the next lecture. The question I'll leave you with is, which of these corresponds to day and night? So some of these distributions will correspond to the day and some of them will correspond to the night. The question I'll leave you with is, which of the 4 distributions I've shown over here correspond to the day and which of them correspond to the night? I will give you a hint. During the day, the surface is going to be hotter than the bottom, and during the night, the bottom of the pavement is going to be hotter than the surface of the pavement. Both are controlled by the amount of sunlight, which is of course 0 during the night. So I will leave you with that question to ponder over, and in the next lecture, I will give you the answer. But for today's lecture, let's continue to understand the climatic effects on rigid pavements, particularly related to temperature. Now, as I mentioned, the temperature distribution in the rigid pavement is going to be non-linear. But what exactly is the actual temperature distribution? What factors determine the actual value of the temperature at some point through the slab? That depends on weather conditions, of course. So it depends on the amount of sunlight, it depends on the amount of wind, depends on the amount of cloudiness, depends on the air temperature. So the weather, of course, has a very strong effect on what is the temperature distribution of the pavement. But then there are certain properties of the pavement layers which also determine what is the temperature distribution of the pavement. So in the next couple of slides, I want to just go through what are some of these important properties which determine the temperature distribution, the exact temperature distribution which is developed through the rigid pavement. And broadly, these properties can be classified into 2 categories: optical properties and thermal properties. So I'm going to define them and then show you how we measure them and what are certain typical values. Okay, so let's start with optical properties. Now, the term optical might seem a little bit confusing to many of you. Optical, you might think of lenses or something which you're seeing, and you might have done some work on mirrors, etc. in high school. But basically, an optical property is a property of a material. Actually, it's a property of a pair of materials. It's a property which determines how radiation behaves when it goes from one medium to another medium. So, for example, if I have 2 mediums over here, medium 1 and then medium 2, and I have some amount of radiation which falls at the interface of the 2 media, part of it is going to be reflected in some way and part of it is going to be transmitted and absorbed in some other way. So the optical properties actually tell us, among other things, what fraction is absorbed and what fraction is reflected, also what fraction is emitted due to in the form of long-term radiation. So the surface properties that determine how radiation behaves when moving from one medium to another are called optical properties. And in the context of pavements, these medium or these media are basically air and PCC, Portland cement concrete. So when we talk about the optical properties of the rigid pavements, what we basically mean is what are the optical properties of concrete with respect to air. There are 2 basic properties that we are concerned with, which is albedo and emissivity. So let me define albedo. Before I define albedo, let me just sort of run a quick thought experiment. Suppose I've got a rigid pavement. I've got the sun over here. The sun is going to beat down on the rigid pavement. So some amount of solar radiation is going to fall on the rigid pavement. Let's call that Q in. As I already said, part of that solar radiation is going to be absorbed or transmitted through the rigid pavement, but part of it is also going to be reflected. If none of the energy was reflected, the pavement would appear black. If all of it were reflected, it would be perfectly white. Only a fraction of it, however, is reflected. So let's call that reflected fraction as Q reflected. This is not reference, this is meant to be reflected. The albedo is a ratio. Note it's a ratio, so it doesn't have a unit. The albedo of the surface is the ratio of the solar energy reflected on the surface to the total incoming solar radiation. In other words, rho, which is a common symbol we use for albedo, rho is Q reflected to Q incoming. We have this value over here. This is what we call the albedo of the surface. We'll look at what some possible typical values of it for concrete are in a second. But one thing I just want to understand, it's not very important to know these in detail, is actually albedo is the average of the spectral reflectance. So although I just talked about solar radiation forming, as I'm sure many of you know, solar radiation is actually a collection of radiation of many frequencies, which is what we call the spectrum of the solar radiation. So the solar radiation spectrum, which I'm drawing up here, might actually look something like this, where this peak value is generally reached for the wavelength generally corresponding to yellow, which is why when we look at solar radiation, it seems to be yellowish color to us, because its peak value actually corresponds roughly to the frequency at which it's yellow. So actually, solar radiation consists of radiation which is at different frequencies or wavelengths. That's what we call monochromatic radiation. So any radiation which consists of energy which is only at a single wavelength is called monochromatic. So the solar radiation is actually a collection of monochromatic radiation. Each of those monochromatic radiation has some flux, which is Q in of lambda. So at each value of lambda, some amount of radiation is going to be incoming and falling on the surface. Part of that will then be reflected. So this rho of alpha represents that fraction of the monochromatic radiation at wavelength lambda, which is reflected. So we multiply rho of lambda by Q of lambda. This gives us what is the reflected fraction, and then we and then we integrate that over the entire wavelength, entire d lambda of the solar radiation. And when we divide it, there's a slight typo here, we divide it by the total incoming radiation, which is Q in of lambda d lambda. Just note there was a typo over here. So this is the total radius. So rho into lambda into Q into lambda is the amount of reflected radiation when that radiation is monochromatic at a wavelength lambda. We integrate that over d lambda to get the total amount of radiation which has been reflected. In the denominator, we just integrate the total amount of radiation, monochromatic radiation, integrated over the entire spectrum, that is over d lambda, gives us the total amount of incoming radiation. So these two basically are equivalent statements. So the numerator here is Q reflected, the denominator is Q incoming. I've just put in a slightly more scientific notation to explain the difference between monochromatic and heterochromatic data. And so this total ratio then gives us the albedo. So this is, strictly speaking, how the albedo is calculated using monochromatic radiation. In practice, however, in the field, when we want to measure the albedo, we just measure the entire intensity of the radiation. So we don't do it wavelength by wavelength. We measure the total amount of incoming radiation and the total amount of reflected radiation. This can be done using an instrument called a pyranometer. Now, a pyranometer is an instrument which basically just measures the amount of solar radiation. It is basically a form of what's called a bolometer, which depends on coming into thermal equilibrium with the surroundings. We won't go into a lot of details, but a pyranometer is an instrument which measures the amount of radiation coming out of a surface. And an albedometer is what we call a double pyranometer. So a pyranometer, for example, would have one sensor which is measuring the amount of radiation coming from a surface. If we put a second sensor on the top, which is actually measuring the radiation coming from the sky, which is the solar radiation, then that particular instrument is called an albedometer. There is a standard called ASTM E1918, and again, you would probably have to go to your university library in order to get a copy of this. But ASTM E19 is a standard method on how to use this albedometer to measure the albedo of a pavement. So what I have an image over here, which is from some work which I had done in the past. Here I've got a pavement. In this case, it happens to be a flexible pavement, but it doesn't actually matter for our applications. But we have a pavement, and this image is the image of an albedometer. So like I've shown up here, it basically has two sensors. There's a lower sensor, there's an upper sensor. The sun is over here. Sunlight coming from the top is being measured by the upper sensor, and then the reflected energy from the bottom is being measured by the lower sensor. So the lower sensor gives you Q reflected, the upper sensor gives you Q in, and so the albedo can simply be calculated as the ratio between these two. So now that we know how to measure albedo in the field, what is a typical value of albedo that we can expect for JPCP sections? Well, here I've got some data which is for a variety of pavements. So if we've got bituminous concrete or asphalt concrete, in other words, if we have a flexible pavement, we expect the albedo, at least initially when the pavement has just been constructed, generally up to 1 year, we expect the albedo to be something around 0.05 to 0.1. Now, what this means is that of all the sunlight which is falling on a flexible pavement surface, 5 to 10% is reflected and 90 to 95% is absorbed. And the reason that the flexible pavement actually looks dark in color or black in color is because the albedo is so low. Over time, however, and I'm sure many of you have experienced this, over time, this freshly laid flexible pavement, it starts becoming lighter in color. The albedo starts increasing. And what has been shown in literature is within about 1 year or so, the albedo actually goes up to around 0.15 to 0.2. So, from an initial value of absorbing some 90 to 95% of radiation, it reaches an equilibrium where it's absorbing only 80 to 85% of radiation. So that's for asphalt concrete. What about for PCC? That is for for rigid pavements. For rigid pavements, it initially starts out with a value of around zero point 0.3 to 0.4. What that means is around 30 to 40% of the solar radiation is reflected and 70 to 60% is absorbed. Compare that to, say, a flexible pavement where only about 5 to 10% is reflected and 90 to 95% is absorbed. You'll agree with me, it's quite a large difference between the two. Over time, however, the PCC pavement also, so the rigid pavement also, the albedo starts decreasing over time, and that's a slightly more complicated mechanism. There are several reasons for that. But it starts decreasing over time. It reaches a stable value around 0.2 to 0.25. Again, these are based on actual measured values, which a variety of researchers, including myself, have done. So that means that over a long time, that is after several years, the rigid pavement absorbs around 80 to 75 to 80% of the solar radiation and reflects 20 to 25% of the solar radiation. So you have to understand that albedo changes over time. For flexible pavement, initially the albedo is quite low. After about a year, it increases to a somewhat higher value. With rigid pavements, the albedo initially is relatively high. It's not extremely high, but 0.3 to 0.4 is relatively high. Over some time, it does decrease, but it still has somewhat of an average value. Now, just for fun and just for reference, I'm sure all of you have seen grass around you at some point. Grass actually has an albedo of 0.3 to 0.35. So although it's not very obvious because grass is green and rigid pavements are a more grayish off-white in color, but at least initially when a freshly laid concrete and grass actually do have a similar albedo, although it's not apparent when you actually look at it. And this is mainly because the albedo is for the entire solar spectrum, not just the visible part of the solar spectrum. So two materials which look different visibly might behave somewhat similar to each other if you also consider what's happening in the infrared part of the spectrum. So that's just a fun little fact I wanted to share with you. Okay, the other optical property which we're interested in is emissivity. So and this actually goes back to what you may have studied in high school in heat transfer classes. I hope you studied this. So as you know, any body whose temperature is above absolute Kelvin is going to absorb and emit some amount of radiation. A body which emits all the energy which is absorbed, that is a perfect absorber as well as a perfect emitter, such a body is called a black body. Now, a black body is a theoretical construct. There are actually no black bodies in nature except perhaps black holes, but that's a different issue. But there are basically no black bodies in practice on Earth. So every body only emits a certain fraction of the radiation at its temperature. The ratio of the energy emitted by a body or by a surface at a particular temperature to the energy which is radiated by a black body at the same temperature is called the emissivity epsilon. And the actual amount of radiation, which is the actual flux of radiation which is emitted, which I'm calling QLW. LW over here stands for long wave. because the wavelength of these tends to be very long. This tends to be mostly in the infrared region, unlike the solar spectrum, where a large proportion of it is actually in the visible region. So this long wave radiation is given by this formula, which is the very famous fourth power law, which I'm sure all of you have seen in the past. Sigma, I hope you remember, is the Stephen-Boltzmann constant, so we know the value exactly. It depends actually on the fourth power law. The net long wave radiation is actually the difference between the radiation emitted by the surface. So the surface has some temperature Ts, and the air also has a certain amount of temperature. So air is also exchanging it's this long wave radiation with the surface. So the net amount of radiation is Ts power 4 minus T air power 4. So this is this fourth power law. How do we measure the emissivity in practice? We use an instrument called an emissometer. An emissometer basically measures the temperature. It has a theoretical value for what the amount of solar radiation is that comes from the Stephen-Boltzmann law. So it has a theoretical value. It measures the actual value at that temperature, and then it gives us the ratio. That ratio then is the emissivity. So we have an emissometer as an instrument. ASTM C1371, in case you're interested, is the specification that defines it. There is no equivalent Indian specification to the best of my knowledge. For PCC pavements, there's quite a large variety which is reported in literature. A typical value can be from 0.8 to 0.95. And I'll show you some graphs and charts which illustrate this. Okay, so here is some work which was actually from my PhD thesis several years ago. So what I have here is I actually had cast around 25 samples of concrete. So these were different types of concrete mixes. So we had different W over CM ratio, which is water to cementitious materials ratio. We had different paste volume, for example. We had different types of aggregates, etc. So there were a whole variety of differences. Some had fly ash, some didn't have fly ash. So we cast a large number, about 25 different mixes, and it was about 3 repetitions each. So as you can imagine, it was quite a lot of concrete that we cast. And we measured the albedo and the emissivity for each of them. And what we see over here, the albedo largely varies in this band, which is the same band I had pointed out, 0.3 to 0.4 roughly. Some values did go above 0.4 a little bit. And then we had another values we measured for emissivity. Here again, you see the lower value actually surprisingly came to quite low, which is 0.5. And then the higher value that we measured was roughly around 0.8. But in literature, people have specified that they've measured something like 0.93 or 0.9. So that's why the range I gave here was 0.8 to 0.95 as a range, but there's quite a lot of variety in the values reported in literature. And there are also some shortcomings in terms of how far in the infrared region you can measure these values. So that just shows you what are the typical values of these materials. So that was optical properties. So optical properties, a reminder, tells you that when sunlight is falling on the surface, what fraction is reflected or emitted, and then what fraction is absorbed. Now, once the energy is absorbed into the surface or transmitted through the surface, it is going to lead to the development of some type of a temperature distribution. How that temperature distribution is formed and how that energy is transmitted or moving through the surface is governed by another set of properties, which are called the thermal properties. So thermal properties govern how heat is conducted through different pavement layers. So the mechanism in this case is conduction, the heat transfer mechanism. There are basically 2 thermal properties that we're interested in, although as I'll show in practice, we combine them into one single value. These 2 are the thermal conductivity, which is in units of watt per meter Kelvin, and then heat capacity. Heat capacity is in units of joules per cubic meter Kelvin, but more usually we use a term called specific heat capacity. Anything specific means it's per unit mass. So that is in joules per kilogram Kelvin. And so generally we show heat capacity as a small case c sub p. So specific heat capacity, any specific property in thermodynamics is shown by capital letter. So specific heat capacity is capital Cp, and the simple relationship between the two is that specific heat capacity is the heat capacity divided by the density, which I'm showing as rho p, of the material. So thermal conductivity and heat capacity. Thermal conductivity tells you the rate at which energy is transmitted through the pavement or through the layer, and heat capacity tells you the rate at which the temperature of the layer is changing for a given amount of energy that has been pumped into it. In practice, however, we generally combine these 2 into one single and very important thermal property, which is called the thermal diffusivity. That's generally shown by the symbol alpha. So alpha is equal to K divided by rho P Cp, is a very, very important relationship. By the way, the units of alpha are square meter per second, although in practice they'll generally be reported in square millimeter per second, so we don't have to write a lot of zeros. This thermal diffusivity then is basically the only value which truly governs the temperature distribution of inside the pavement once energy has actually gotten inside the pavement. That is based on the optical properties. So how do we measure these thermal properties? There are broadly two ways to measure thermal properties. There are steady state methods and there are transient methods. Now, steady state methods are basically a class of methods where we allow the body to reach thermal equilibrium. A very common one, which is generally called a guarded hot plate technique, for example, if you're measuring thermal conductivity, is we take, let's say, a rod of a particular material, or if it's concrete, it could be a beam. We insulate two sides of it. We put in some amount of, we pump in some amount of radiation or some amount of energy on one side, and the other side we leave it open, so some amount of radiation energy is going out from the other side. Eventually, this will reach some type of a temperature distribution after a long time. So what we do is we run this test and we leave it for a very long time, and then we measure the temperature distribution, and then we can calculate the thermal conductivity from there. This is called steady state because we've had to wait a very long time, and this can actually be several days to even a week that you have to wait for the test to run. So that's a steady state method. There is another technique called differential scaling calorimetry, which you can use for CP, which is also a steady state method. So the problem with steady state method, well, the advantage of steady state methods is they tend to be fairly accurate. There's no approximations you have to make in them. But the problem with them is they're very slow. You might have to wait for a day, several days, or even a week to conduct one test. So then we have another class of methods called transient methods. I won't go into a lot of details, but a particular case of a transient method is what's called a hot disk instrument. So this is an example, again, from some of my work which I did, that we have a specimen. This was a flexible specimen, but we also did it for concrete. This was a specimen, and we have this hot disk over here. This basically applies a very small amount of energy to the surface, and then also measures, as a function of time, it also measures what is the temperature. So it gives us a temperature versus time plot. And then based on that, using some curve fitting, K and CP can be evaluated using the same test. So this is a transient method because you are actually measuring the temperature change as a function of time. Advantages, it's a very fast method. You only really have to run this for a couple of seconds, and you have to wait maybe 10-15 minutes for it to reach thermal equilibrium. But the disadvantages, there's some curve fitting involved in this process, so you have some approximations in this whole process. And here is some data from work that I collected for rigid pavements. Average thermal conductivity over all those specimens I showed is around 2.2 watt per meter Kelvin, and average diffusivity can be 1.5 square millimeter, please note the unit, square millimeter per second. So this is from this paper, which I published in 2019. Okay, so that concludes what we wanted to talk about today. So I wanted to talk about temperature and climate effect, climate, which means moisture and temperature in our discussion. I want to talk about climate effects in general and how they affect rigid pavements. Now, as you may have noticed, today's lecture, it was fairly qualitative in nature. I gave you a lot of information. We had some very interesting discussion also, but I never told you how to do any hard calculations for this. Ultimately, when we talk about performance of the pavement, of the rigid pavements, we want to know what is the stress developed in the pavement. That's why we studied Westergaard's theory. That's why we did the Freiberg equations. We are interested in calculating stress. So it's all well and good to be able to understand qualitatively the effect of temperature. But in the next two set of lectures, we are going to talk about how to quantitatively calculate what are the stresses developed in the pavement as a result of moisture, as a result of temperature. In the next lecture, we will talk about a particular effect which comes from temperature, and that's what we call curling. And in there, we will see particularly how these non-linear temperature distributions, which I mentioned in today's lecture, how these non-linear temperature distributions contribute to stress. I will also answer the question on what distribution corresponds to day and what distribution corresponds to night. So I will see you in the next lecture. Thank you.